We're delighted to have him here talking tonight about the importance of returning astronauts to the moon. So, with that, David, thank you so much for joining us. You have to click on the button.
Thank you, Christine, and I'm certainly glad to be here. If there is, I'll pause for just a moment to make sure there isn't something else you need to say. Otherwise, I will go ahead and start talking about tonight's subject.
I think we're ready. If you have other things about yourself and what you've been studying that you'd like to add, you're welcome to do that as well.
No, I think I'll simply begin tonight's subject, which is um, really outlining or summarizing the case for our nation's lunar exploration program. And there's going to be a historical component to this, and that I think it's important for people to understand. I then want to describe where we are in that exploration program, what we hope to learn from that exploration program from the point of view of a scientist, and then we'll open the floor up for lots of discussion so that this evening's activities really revolve around people's questions. Our nation's return to the moon began with a national security assessment of our nation's space program, and it was recognized that our program is not accelerating at the pace of other nations around the world. It was also recognized that our economic position in the world was not accelerating, or in some instances even remaining static with other nations in the world. And so it was determined that we should reinvest in our space program because of the lessons of Apollo. It's a historical fact that Apollo drove technology in this country to new levels, that fueled the economic engine of this country, and that in fact has assured Americans a wonderful quality of life for the last 30 to 40 years. And so the idea behind a reinvigorated space program was essentially to create an opportunity where our nation could regain those technological edges, or to stimulate new technology in this country. Exploration by and in itself is also important, I think, to the fabric of our nation. And I think I would like to actually quote from the vision for space exploration as it was outlined in January of 2004. It begins, "Mankind is drawn to the heavens for the same reason we were once drawn into unknown lands and across the open sea. We choose to explore space because doing so improves our lives and lifts our national spirit. So let us continue the journey." With that phrase, there were very specific targets given to the nation. And specifically in the context of the moon, we were given 4 targets. To first, undertake lunar exploration activities to enable sustained human and robotic exploration of Mars and more distant destinations in the solar systems. That is, we are going to the moon so that we are better able to go farther out into the solar system. Second, starting no later than 2008, we will initiate a series of robotic missions to the moon to prepare for and support future human exploration activities. 3, conduct the first extended human expedition to the lunar surface as early as 2015, but no later than the year 2020. And fourth, use lunar exploration activities to further science. We cannot overlook the importance to science, and to develop and test new approaches, technologies, and systems, including the use of lunar and other space resources, to support sustained human space exploration to Mars and other destinations. This last bullet actually captures, in some sense, the technological drivers and the economic advantages that the space program is hopefully going to generate. That came from an evaluation of our space policy by the executive branch of the government. It was briefed and debated in the legislative or congressional branch of the government, and in a surprisingly large bipartisan support, the Congress reauthorized NASA, rewrote the language that governs NASA, and told NASA in no uncertain terms to design new systems to take us to the moon and beyond. And so our nation, led by NASA, has been on that path for over 5 years. NASA has been exploring different exploration architectures, different science architectures, and has begun the robotic program, and has begun the design phase for the human program. As many of our listeners may know, the Lunar Reconnaissance Orbiter has launched and is successfully in lunar orbit, generating the data that will be needed for future human exploration, and at the same time creating some wonderful science. And those scientific results, I think, will start to appear in early March at the Lunar and Planetary Science Conference here in Houston. Some of the hardware components, the major hardware components, are also being built. The Ares 1 test rocket, which is the vehicle that will carry crew to space, has had a test flight. That test flight was earlier this year and was quite successful. We've also been designing a lunar electric rover. This is a pressurized vehicle that will allow crew to travel much greater distances over the lunar surface. We've conducted 2 lengthy lunar mission simulations with that type of vehicle, and in fact, just tomorrow here at the LPI, there will be a next generation design phase for that lunar rover, and another extended lunar mission simulation is planned for later in the year. So NASA and the scientists and engineers who work with NASA, myself included, have our marching orders from our government, and we are trying to move forward as best we can with the budget that we have. So I think that outlines the scope of the exploration activities. I would like to say something about our science objectives, but I think this is actually a good moment to pause and begin to get feedback and answer some questions.
Sounds good. So folks, if you have a question right now, please go ahead and either use your microphone, or if you'd prefer, you're welcome to type it in under the chat here box or the enter your questions here box. And it looks like Michael has a question here about when you give public talks or lectures, uh, is the general public aware of the project Constellation and America's plans for returning to the moon? Have you discovered that most people are aware or aren't really aware of these things, David?
It's fascinating and in some sense disappointing. In general, the public is unaware of the Constellation program, and for those of you listening who may not recognize that term, the Constellation program is basically the modern version of the Apollo program. It is the program, the umbrella under which we are going to go to the moon and beyond to Mars and so on. People during the 40th anniversary of the Apollo 11 landing earlier this year certainly became aware that there was some discussion as to the exact path to the moon and beyond to Mars, but they actually saw it as a debate, as an undecided situation. They had very little grasp that this was something that had been outlined and made the law of the land over 5 years ago, and that in fact hardware was already being built. One of the other hardware elements that I didn't mention a few moments ago is the launch facilities. One of the launch facilities for the space shuttle has been completely turned over to the Constellation program, and for rephasing and redesign to support the Ares 1 and Ares 5 components. So um, hardware and equipment and operational plans are being put in place. So we're already long on the road of the Constellation program.
While we're waiting for the others to think of their questions, what do you say to those who have argued that we've been to the moon and it's just difficult to get the public excited about going back?
There's actually a large number, a surprisingly large number perhaps, of answers to that type of query or confusion. Um, One of the things that I point out is that the Apollo astronauts, and even if one includes the Luna spacecraft of the Soviet Union, only touched down and operated in a very small region of the moon. If you were to draw a line around all of those landing sites, it's only 4 to 5% of the total surface area of the moon. And of course, at any one of those sites, their mobility was greatly limited, and so they actually weren't able to see very much. And so it would be really hard to argue that we understand the moon based on that limited exploration. And to give an analogy, if you were to suddenly land, if you will, in the Boston Garden or land on the mall in Washington, D.C., and walk the lengths of those two locations, you would not be in a good position to describe the geologic or biologic history of our planet. You would know nothing about the Sahara. You would know nothing about the Amazon. You would know nothing about Antarctica. And so such a tightly restricted or limited amount of exploration really doesn't clue us into the things that uh, uh, wait for us to learn and to discover on the lunar surface. We know nothing about the lunar poles. We've never been to the lunar far side, just to list two major areas of the moon that need exploration.
Thank you. Alan's asked a question here. Why do you think the idea of constellation received so little traction, and why did they pick the name constellation for returning to the moon?
I actually don't know the origins of the name constellation, so I'll have to simply beg off on that. But why hasn't constellation gotten more traction? Um, I think partly that is a public communication problem that NASA and its partners, myself included, have had. We just haven't been successful, or I haven't tried hard enough. Um, Part of the problem that we have, one of the issues that we have to be careful of, is that during Apollo, there was just the Apollo program. There was a clear ramp up. In this case, we also have an existing shuttle and International Space Station program. And so not all of the announcements, not all the public announcements, not all of the EPO, education and public outreach activities, can be focused on the Constellation program. And so there is some dilution of attention. Simultaneously, we do have a wonderfully rich robotic program led by the Science Mission Directorate at NASA, and that certainly fascinates the public. But again, it is in some way occupying a part of the message pipeline to the public. And that type of competition isn't bad. We actually want a healthy and robust exploration program of the entire solar system, but it does mean that the amount of words that one can convey about the constellation program is less than one could have conveyed during the Apollo program.
And Michael has another question. What are your thoughts on the projected gap between the space shuttle and the constellation? And are there alternatives you think haven't been considered?
Well, in some level, that's a strategic issue that hasn't gotten much of my personal attention. like a lot of Americans, worry about the fact that we will not have a major lift capability. I would like that gap to be shrunk to as small as possible. But of course, in reality, what that really requires is budget. And NASA just simply does not have the budget to narrow that gap. So in some sense, it's a matter of will. If Congress or the American public insisted that gap be closed, it could be closed a little bit. I have to say, at this late point in time, that gap I don't believe can be closed altogether. And the longer into this process that we go, or the closer we come to the end of the shuttle launch capability, the uh, inability we will have to close that gap further.
One of the areas that you've been researching is the cataclysmic hypothesis, although it's got quite a bit of data behind it. I don't know if it's really considered a hypothesis these days. And I was wondering if you could say a few words about why the science studying the impacts that occurred on the moon is important to us these days.
Yeah, that's a good question, Christine. And I think actually it might be useful to briefly introduce all of the major hypotheses that the Apollo program and post-Apollo analysis have given us. And a hypothesis, by the way, I think is the right word. We may have a lot of supporting data, but one of the reasons we need to go back to the moon is to rigorously test these hypotheses. Um, in chronological terms, the first hypothesis is the giant impact hypothesis of the moon. Uh, right now, our best understanding of the origin of the moon involves the collision of an object twice the size of the moon with the early Earth, and that impact event generated an ejecta cloud that was in orbit around the Earth that then accreted relatively quickly into the moon. The second major hypothesis is the lunar magma ocean hypothesis, based on analyses of Apollo samples. In fact, the first Apollo 11 samples, it was an extraordinary scientific feat. It was deduced that the moon may have been so hot soon after its origins that it was essentially a molten sphere in space, and that as it cooled and crystallized, it differentiated. Towards the end of that differentiation phase, one of the last phases to crystallize, feldspar or plagioclase feldspar, floated to the top, forming the bright white highland crust of the ancient moon. And then again, chronologically, the third major hypothesis is, as you mentioned, the lunar cataclysm hypothesis, which is a hypothesis that suggests that the moon was severely bombarded in a narrow interval of time about 4 billion years ago, after a relatively quiescent period of bombardment that may have stretched over about half a billion years. The problem that we face with that last hypothesis is we have a limited number of samples from a small area of the moon. Uh, Moreover, that small area of the moon has been greatly influenced by 3 of the 50 basin size impact events that affected the lunar surface. And so we worry that the Apollo sample data is biased by those 3 impact events. And so it behooves us to determine the ages of large impact craters elsewhere on the lunar surface, and in particular, determine the age of the South Pole Aitken Basin near the South Pole on the far side of the moon, which is the oldest and largest impact basin on the moon, and arguably the largest crater in the entire solar system.
And for your average American, they need to, we would like to know more about this because what will appeal to the average American about why we should know these things?
There's several levels of answers to that question. First is kind of a selfish answer, and that is what happened to the moon in terms of its bombardment history happened to the Earth. The moon is essentially in the same part of the solar system as the Earth, and so whatever cascade of impacting objects resurfaced the moon was hitting the Earth at exactly the same time. The age of this hypothesized bombardment is very interesting because it immediately precedes the earliest evidence of life on our planet. And so scientists over the last 20 years have wondered whether this bombardment may have had some effect on the origin and early evolution of life on our planet. So uh, in a very real way, by going back to the moon, we will better understand the early evolution of our planet, including the early evolution of life on our planet. Um, so determining the timing and the magnitude of that bombardment is going to be very important. The bombardment that affected the Earth also destroyed most of the terrestrial rocks that were in the crust of the Earth at that time. And so we also hope by going back to the moon that we may find a few remnants of those early terrestrial rock samples, because the same bombardment process that was destroying the Earth's surface was launching fragments of the Earth's surface into space, and some of those fragments may have landed on the lunar surface. The moon, because it's a smaller planet and cooled, and magmatic activity has largely ceased, has a much better preserved ancient record. And so any of these early processes are going to be much better preserved on the lunar surface than they are on our own planet.
Thank you. We have a couple new questions typed in. Michael wanted to know whether there are areas here on Earth, particularly in the United States, that are geologically and or physically similar to the moon.
That's a good question, and in fact, we in the business refer to those as lunar analog sites. And to first order, in general terms, um, any basaltic volcanic site and any impact crater terrain are plausible analogs for the lunar surface. One of the classic lunar analog sites that was used extensively during the Apollo program is the Flagstaff, Arizona region. Not only does it have an extensive field of basaltic volcanics, lava flows, and cinder cones, it also nearby has an impact crater, the world's best preserved impact site, Meteor Crater. And so in one location, a relatively small area of the Earth's surface, one can train astronauts and test equipment and practice geologic activities in a lunar analog terrain. Now, during Apollo, astronauts were also trained in a large number of other places, Kilburn Hole in New Mexico, the Pinacate volcanic field in northern Sonora of Mexico. Trips were taken to various sites in California and in Hawaii, to the Sudbury Impact Crater in Canada, to Iceland, to the Reese Crater in Germany. But despite the global extent of the training activity, most of it was done in the American Southwest, which is an arid terrain, very little vegetation, so the geology is spectacularly preserved and provides a good training opportunity for our astronauts.
Andy's got a couple more questions, but before I ask them, does anyone else have something they want to ask out loud? You're welcome to use your microphones. I guess not right yet. Andy wanted to know where did the impactors responsible for the late heavy bombardment originate, and what are the different competing ideas about that?
Well, let's first talk about choices. Our choices are essentially the asteroid belt, um, comets, or Kuiper Belt objects. And some people would lump comets and Kuiper Belt objects into the same category, but nonetheless, we have, I guess, in some sense, two populations of objects: an inner solar system population of relatively rocky objects, and an outer solar system population of objects that are mixtures of ice and rock. If one looks at the Apollo samples and tries to detect the chemical fingerprints of the impacting objects that produce the impact melts, one oftentimes sees fingerprints that point to asteroids as opposed to the icier comets. This actually was visible in the data that was collected during the Apollo program, although it's been clarified and expanded by more modern teams using more modern techniques. In addition, there's a geological fingerprint. If one looks at the size distribution of the craters on the lunar surface, and for that matter, the southern ancient cratered highlands of Mars, that size distribution seems to suggest that the size distribution of asteroids is a more likely match as opposed to the size distribution of comets. Um, in fact, that latter data has an interesting component to it in that it suggests that the asteroid belt was sampled in a size independent manner. Uh, the only way that we know to sample the asteroid belt in a size independent manner is for gravitational resonances that perturb the orbits of asteroids equally, independent of size, need to sweep through the asteroid belt. Well, those gravitational resonances are dominated by and created by the gaseous giants, in particular Jupiter. And so the requirement that resonances sweep through the asteroid belt actually implies that Jupiter's orbit shifted. Um, Now that's really the point at which there's a lot more room for speculation and competing hypotheses. What caused Jupiter's orbit to move? And they basically fall into two categories. On one hand, it's suggested that the orbits of the outer solar system planets were different than they are today. They were in a metastable state, and that about 4 billion years ago they suddenly reorganized themselves. It's even been suggested that Uranus and Neptune's orbit used to be inside that of Jupiter and Saturn, and that they switched places, if you will. The other hypothesis is that, in fact, maybe Neptune and Uranus had some type of delayed accretion. Um, Potentially going back to the moon, and analyzing additional impact melts, we'll be able to test those competing hypotheses and resolve this issue.
Another question was, what lessons from Apollo are used to prepare astronauts for future moon landings?
We actually are in the initial stages of writing the curriculum for the future lunar astronauts, and there will be a classroom component. Just like a beginning geology student, we need to introduce crew to the different types of rocks so that they can identify those rocks. They need to better understand uh, what those different types of rocks imply about geological processes or the evolution of the moon. And the reason for this is we want them, of course, to be smart enough to recognize the key samples or the key outcrops on the lunar surface to investigate. We also need to take them to these analog terrains, volcanic terrains and impact crater terrains, so that they can see uh, the topography of these features, recognize the distributed geologic structure and the features in different places in these types of environments, so that when they land next to an impact crater or land next to a lava flow on the lunar surface, they'll know exactly how to go about exploring that particular feature. But I have to say that the training has a very important scientific component to it, and an intensely geologic component to it, because the lunar surface is inherently geologic. But there is also an operational component to the training. Crew need to learn how to do geologic activities in spacesuits. They need to learn how to do geologic activity from unpressurized rovers and pressurized rovers. They need to learn how to collect appropriate amounts of samples and to curate that material for safe return to Earth. And so, and something that's oftentimes overlooked, the crew has to learn how to work with experts who will be backing them up here on the Earth. With Apollo, we had what was called a science backroom, and we will have something akin to that during the Constellation program, where there will be a group of scientists quite expert in these processes and in the lunar surface, helping the astronauts from afar explore their terrain and learning how to communicate, learning how to understand each other over vast distances using perhaps limited amounts of imagery is difficult. And that type of operational training is actually underway already.
Our next question is, what improvements are coming in lunar spacesuit design, and will future astronauts have freedom of the hills?
Two very good questions. With regard to spacesuits, the spacesuits are going to have a lot more mobility for the astronauts. The details of that mobility are still not yet known. But the Apollo spacesuits were designed in a very limited way. Basically, it was understood that the crew would be on the surface for no more than a few hours in these spacesuits, and so they weren't very resistant to abrasion, and they had limited mobility, and they were that because of that limited mobility, they were actually brutal on astronauts' bodies. And so, if we're planning a long-term exploration of the lunar surface, we simply have to have a spacesuit that is astronaut friendly. And so that spacesuit design process is underway. A contract's been awarded to a company that is working with NASA to develop that spacesuit. Um, and the second part of that question, the second question was, will future astronauts have freedom of the hills? And not initially. The hope is that they will in the end, but initially they're going to be on the lunar surface for relatively short durations as we test the hardware, as we test our new communications and operational systems. And so those initial missions are likely to be fairly scripted with nice, tightly designed traverses and station plans similar to Apollo. But as the program evolves and astronauts actually get to spend longer periods on the lunar surface, perhaps months, then it is hoped that they will be able to act as their own field geologists, still supported by scientists back here on Earth, but given a lot more flexibility. It's easy to imagine that an astronaut, after spending 2 or 3 weeks on the lunar surface, is the de facto expert on the geology of the lunar surface. And so, like a PhD student in their particular field area, they are going to be able to make the best and most appropriate decisions. So that's the long-term goal.
Our next question is, do you have a favorite Apollo lunar mission? And if so, why?
Well, yes and no. I mean, everybody's favorite has to be the Apollo 11 mission because it was the first time that humans touched down on the surface of the moon and returned to Earth safely. I mean, that was a spectacular feat in human history. It also was the mission that immediately uh, gave us all of the major scientific highlights of Apollo. It was the samples collected from that mission, for example, that led to the lunar magma ocean hypothesis. It was that mission, for example, that taught us, without a doubt, that the circular features that one sees on the lunar surface are dominantly impact craters rather than volcanic craters, which was one of the big controversies prior to the Apollo landings. Beyond that, I have to say that Apollo 16 and Apollo 17 fascinate me because they allowed the astronauts to address some very important questions about lunar bombardment. Truth be told, I've studied samples from every one of the Apollo missions, and they're all fascinating.
And now our next question is that there's been a long controversy about whether it is better to have humans exploring the moon, robots controlled from Earth, um, or telepresence with robots controlled by astronauts in safety in a habitat. What sorts of work and exploration can only be done by humans on the surface?
Um, I I understand the question. In fact, there's been a tremendous debate historically in this country about the relative values of robotic exploration and human exploration. And I have to say right up front that I don't see it as a one or the other. I don't think it's a polarized or type of situation. And I think that what we're going to find as we seek a long-term, if not permanent presence on the lunar surface is that one has to have integrated robotic and human systems. The level of that integration is actually going to be different in different phases or of the exploration activity or at different sites on the lunar surface. So for example, there is going to be some mechanical or resource intensive activities on the lunar surface that could, we think, be dominantly robotic, driven by robotic activity. Whereas the subtle science or the decision making activity before things are deployed are the types of activities that you really need a crew for. Um, they can see and make interpretations of what rock to pick up far more efficiently than a robotic component. My vision of some of the early human missions is one where there will be a robotic precursor, maybe scout some traverse options, perhaps even explore a couple of candidate station sites, collect some in situ data that can be used to reformulate the landing plan. Once crew gets there, they do their Apollo-style activity, and then after they've left, they can reactivate, or humans from Earth can reactivate those robotic components and follow up on the exploration that the astronauts did. Perhaps we get a sample that comes back to Earth that is particularly interesting, and we decide we need to go back to that outcrop and better understand the context of that sample. And that's the type of thing that can be done from Earth using robotic assets. When the length of the mission increases to month-long durations, then the integration of those of robotic and human components is going to change yet again. So, for example, if a crew is having to spend the 14-day-long lunar night on the surface, they may be restricted to the habitat, and during that time, they could actually explore other areas of the lunar surface using a robotic asset. And so you can envision this as being an extension of the astronaut and as an astronaut assistant.
Right. Thank you. Um, how detailed will the landing site knowledge be from the orbiter or other means of exploration, and how much help will there be there to plan the surface activities?
That's a question that actually oftentimes causes a lot of concern within the operational planning divisions of NASA. Um, I think that our understanding of the lunar surface, well, I think it's clear that our understanding of the lunar surface, any particular landing site, is likely to be far better than it was at the time of the Apollo landings. The Lunar Reconnaissance Orbiter, which is currently in place and collecting data, is going to provide in many locations, albeit small areas, resolution with basically half-meter resolution. And so I think that our orbital or remotely sensed interpretation of the surface will be equal, if not much greater than that of Apollo. But as Apollo demonstrated, there are going to be surprises once we get on the lunar surface. So we just have to be prepared for that, and in fact look forward to it, because it's those surprises that turn out to be the most interesting science.
Do you think an astronaut would be able to do their dissertation and receive a PhD for their work on the moon?
Uh, they could. They've not traditionally done that. I have to say a couple of things along those lines. One, although they never were given certificates or given degrees, it is often said that the Apollo astronauts had the equivalent of a master's education in geological sciences based on their training. Um, it is in the current baseline plan for Constellation that in each crew of 4, 2 of those will be professionally trained geologists, and the other two will be trained in geology. So we will already have, I guess to say it more clearly, 2 of the crew, or half of the crew, will already have their PhDs in geological sciences.
Um, about scripting of human activities on the moon, it is hard to believe that flight controllers will give up their absolute control over timelines. Have your simulations of human missions ever generated conflicts between the flight controller and the astronaut in the field?
Yes, actually, our simulations have done that, in some cases intentionally, and at other times at unexpected moments, unintentionally. So that is one of the um, reasons for the simulations, is to determine uh, what will happen, what range of possibilities exist, and more importantly, to test or train, excuse me, both the crew and the operational people um, how to communicate well and operate in those environments. There are some things that we are having to wrestle with. So, for example, the um, quality of the analytical equipment that we should be able to deploy on the crew rover is going to be so advanced that there are going to be times when the scientist in the science operations room will have more information than the crew. Now, those are going to be, I think, rare moments, but at those when those times occur, there has to be a way of the science operations room of conveying that to the crew so that they can work efficiently together. And so, yes, we've run into that activity a couple of times, and it's one of the things that we are going to continue to explore with these simulations.
And the last question I've got listed right now, aside from the human expeditions of Project Apollo, what is the most significant achievement or event or scientific discovery gained from the moon?
Um, I think that this is one of those questions that has a lot of reasonable or rational answers. And so I'm imagining, for example, if this question were to be asked of Carly Peters at Brown University, she would give an answer that may be distinct from mine. If you were asked Jeff Taylor at the University of Hawaii, he might give an answer that's distinct from mine. But since I'm here and the question is asked of me, let me give you my spin on that. Um, with Apollo, there was a tremendous amount of discussion as to whether the surface was dominated by volcanic geologic processes or impact cratering geologic processes. And we now know that both operated and influenced the lunar surface, but the punchline there, the take-home message of Apollo was that most of the circular features on the lunar surface were in fact produced by impact cratering processes, and that impact cratering process is the dominant geologic process affecting that type of planetary surface. And that really has shaped and guided a lot of science throughout the solar system as well as on Earth. The density of craters, for example, has allowed us to determine the relative ages of geologic surfaces on other planetary bodies. What we know about the chronology of Mars, for example, is largely driven by our lunar exploration activities. In addition, it basically created a scenario where the scientific community, uh, composed in this case of geologists and physicists, actually had the capacity, had the breadth of exposure to this concept to actually hypothesize that the mass extinction event at the KT boundary, which claimed dinosaurs and most living organisms 65 million years ago, may have had an impact origin. That impact mass extinction hypothesis has subsequently been sustained or confirmed with the discovery of the Chicxulub impact crater in Mexico. And that type of intellectual advance, the understanding that impact cratering is an important geologic process, and further that impact cratering can affect both the geologic and biologic evolution of a planet, is something that Apollo delivered to us, not directly, but it set the stage. And that's the power of exploration. It changes the way you think. It gives you unexpected information, and the benefits are always a surprise, and an astounding and beneficial surprise.
Right. Well, folks, it's your last chance, especially those of you who haven't asked a question yet or had something that you wanted to share. We'd love to hear from you. We have a question from Michael. Has the International Space Station ever been used for lunar observation or research?
I'm not in a very good position, I have to say, to answer that question. I suspect, but I don't know, that some of the imaging systems have been periodically trained, if for no other reason an astronaut was curious, towards the moon. Has something serious or significant been accomplished with those top ISS-based observations? Not that I know of, but I have to plead ignorance on much of the science activity that's been done on the ISS.
There is that common misconception that it's quite a bit closer to the moon when in fact it's hardly closer at all. So aside from the fact that it isn't dealing with Earth's atmosphere, it doesn't really have that much more of an advantage over the rest of the telescopes. Um, if you were given the opportunity, would you be headed to the moon?
I think so. It is important and great fun to work on the lunar simulations, to train staff involved in those operations, to train people who may be crew or in the end may be trainers of crew. Um, but it's also true that there are a few geologists in the NASA sphere that have tremendous amount of experience in both relevant volcanic and impact crater terrain, and I think it would be truly astounding if people with those capabilities had an opportunity to spend even a short amount of time on the lunar surface. I, I mean, just in a very simple sense, could imagine a tremendous amount learned by simply spending a day or two in a small 1 kilometer diameter crater on the lunar surface with the eyes of somebody who has experience with that type of structure and collected samples from that type of structure and done all of the isotopic and microscopic analyses of that type of sample. I think that there would be a significant scientific gain. But there's more to being an astronaut than just having the scientific training. It takes commitment. It takes physical endurance. It takes the right personalities. Aptitude is very important. Um, and an aptitude to work in an operational setting is absolutely key to success. And that's a type of activity that doesn't lend itself to all or even most scientists. It will require a special group of people.
Well, it looks like our time has just shot past really fast. Um, Dr. Kring, I do want to thank you for your time and your and all that you have shared with us. Ladies and gentlemen, does anyone have any final words? We have one last question here, and that was based on your experience at the NASA Space Imagery Center in Arizona. Has imagery evolved from our earliest? How has our imagery evolved to today? The resolution, the camera equipment, etc.
Well, the technology has changed dramatically. During the Apollo program, we had real cameras with film. And in the case, at least of the orbiters, that film was not brought back to Earth. The orbiters crashed on the lunar surface, and so they had to be electronically scanned, and the electronic scans that sent back to Earth, and they were stored on magnetic tapes. The resolution, I have to say, of that type of imagery was extraordinary. Some of the lunar orbiter images have meter scale resolution and are can't be beat, even with more modern missions having flown to the moon. There is our ability to do digital imaging is going to change surface activities. On the Lunar Electric Rover that we've been using in our simulations, we can put an array of those types of imaging systems on the rover, and it gives both the crew and the operational staff back on Earth an extraordinary amount of information, high resolution information, and I think that is going to change the way we do business on the lunar surface, and our simulations are just now exploring what those changes will be.
Well, thank you so much for your time, David. And everyone, thank you for joining us. We do appreciate it. We hope to see you again here soon. Same bat channel, same bat time.